So, what I am going to discuss today is some really in some sense really some concrete example of what explicitly a generating function looks like for Hamiltonian symplectomorphisms, at least when they are sort of close to identity. Now, there is some problem in the notation that I am going to use and what Yasha uses. So, I will point out it is related to what Yasha says, but not exactly same. Okay. So, I will point out, but therefore, let me define my setup. So, as usual, let us take so let me write here. I have R2n with my symplectic form and where I am giving R2n coordinate okay. And just like Yasha, I am going to write for any product of the type summation say x I dy I or something as just x dy. So, that we can just pretend that we know things about R2 and everything goes through, okay. But it would typically mean x I dy I. Okay. So, let me first define. So, let psi be a symplectomorphism So, let psi be a symplectomorphism and suppose there exists a function S from R to n, but now for this R to n which I am defining a function, I will give a coordinate x comma u, because you have seen that whenever Yasha is doing generating function, there is some coordinate transformation is involved. So, it is confusing to just all the time call R to n with the same coordinate. So, I am making new coordinate x comma u. I mean, I could have made u1 comma u2, but I will tell you why I am saying it x comma u, because the first coordinate I do not need to change. Okay. So, think of this as a function from R to n which has coordinate x comma u. Okay. So, that is just for convenience. So, suppose there is a function S from R to n to R which satisfies the following. So, psi of x y is u comma v if and only if y is okay. Suppose this symplectomorphism has a property that psi of x y is equal to u v if and only if this y coordinate is ds by dx of this function and v is ds by du. Okay. Then we say that S is a generating function. Okay. So we say that this is generating function if this y coordinate is coming from the x partial derivative of s and v is coming from the, so v is v of x y. So, this for psi x y is u x y comma v x y. Okay. Now, so note that this definition of generating function essentially does exactly what Yasha has been doing up to some coordinate change, because if you write, so what is the, with this definition what is psi is actually psi of sorry, this is minus psi of x minus ds by dx equal to u comma ds by du, which implies that this is like, if you look at graph of psi, it look like x and which is what we are looking at, which is like d of s, because this is the derivative, this is the graph, this is s is a function in u and v variable. So, this is d of s. Yeah. So, up to coordinate change. So, but one thing here is important, that since I want, so I have psi x y is equal to u comma v, if and only if this, it means, and I want u to be a variable of R 2 n for s to exist, that means the map. So, implicit in this definition is the fact that the map is a diffeomorphism. So, therefore, I can express, instead of coordinate x comma y, I can express R 2 n as coordinate x comma u, and then everything makes sense. Yeah. Is it clear? So, now of course, so now if you look at, so thing to observe is that, so observation is that if I look at the d psi, the derivative of psi at any point, and if I write it as a some matrix A B C D, where I am looking at this matrix is obtained using the fact that you have coordinate x and y, x1 x2 xn x1, then for this to be at least locally invertible, to give at least a local coordinate chart around x naught y naught, or implicit in this definition is that this is diffeomorphism, and this means for every point this d psi has this property that this b determinant of b, since is diffeo, this determinant of b is non-zero. Okay. Because unless the y coordinate of u is non-zero, I mean this cannot be diffeomorphism. Yeah, that is a sort of necessary condition. So, what I want to first prove is that, suppose I have a symplectomorphism that satisfies this property, then there is always locally a generating function. No,
you want D non-zero.
Huh?
Don't you want determinant D non-zero?
Determinant
D.
Ux y is y मतलब
Last condition.
yeah, but x y going to x y identity function can have generating function, no?
Yes. So why do you want determinant D non-zero?
No, but yeah. So that's what I am saying. That this is the so you determinant D non-zero, no? Yeah. So determinant D non-zero function is what he assumed, and so that's what this was the precise point where I said that the coordinate how I am using has this property that either you can assume this determinant D non-zero or determinant B non-zero, and then there is some coordinate transform. So in my generating function, for example, identity which he got as a p times q some generating function is does not come by this condition. So you just have to check for any psi, there is no unique procedure. If determinant D is non-zero, whatever I am going to carry out, but in that case x y going to x v will be a invertible function, and correspondingly you will get a generating function with a coordinate r and x and v. So I am just doing one of them. Either you assume that x y going to x u is or y comma x y going to x v is non-zero, and accordingly you can change the variable which he was talking about. So he used the coordinate v, I am using the u, but there is, I mean there is no different difference philosophy. Shall I continue? So here, okay, I have next remark is what Mahan asked, that you can assume that determinant D is non-zero, and this is what Yasha did, but anyway now I explain. Okay. So that corresponds to different choice of parameterization and okay. So now I want to first show that under the assumption, so this is under the assumption that this was non-zero everywhere, but suppose I have some point x naught y naught under where I know that around this neighborhood d by du dy is non-zero, that means at least I can locally invert. Then I want to show that once you locally invert you have a generating function. Okay. So at least locally you can get generating function, and that is my this next lemma. Suppose I have a symplectomorphism, and suppose for some x naught y naught in R2n omega naught, psi of x naught y naught is u naught v naught in R2n, and if for then for every x naught y naught, then for x naught y naught in R2n there exists a neighborhood u x naught y naught of x naught y naught, and such that psi x y going to has an inverse, sorry, and the function such that the function phi x y going to phi x u x y has an inverse, and therefore, I will find some neighborhood, hence there exists a neighborhood u which will depend on x naught and u naught, the value, hence there is a neighborhood u contained in R 2n with coordinate x u and a function S from to R which generates psi locally around x naught y naught. Okay. So, it means the if I am given a pair of number x and u, I will be able to recover the y coordinate there and v coordinate there, okay, by some function's partial derivative. Is it clear? So, this is just a simple calculation. If you want to think, you can think of just graph of psi of x as a thing inside R n cross R n cross R n cross R n, and this u naught is some appropriate intersection with diagonal. Okay. So,
last slide was what is the function
no, phi I am just saying that since this determinant is non-zero, this x y going to x u x y is a invertible function, and I will write its inverse as some other function, which I will come to that. So, phi is just a function that sends x comma y to x comma the first coordinate function of original psi. Is it clear? Just like we had in the definition, we are just using the definition, but implicit in the definition of the fact that there will be such a generating function if this function is invertible. So, we say that locally invertibility means that some determinant of some matrix is non-zero. So, I assume that, then I will get some diffeomorphism. Is it clear? And that would act as my coordinate change. So, this is the coordinate change function. So, from x y now I will call it x comma u, and I will write everything, I will define a function s and I will write everything in terms of dx and du, not in terms of dx and dy, and then when I write it in terms of dx and du, I see as a d of some s. So, it is finally a matter of seeing some graph as a d of s. Okay. So, this let us call that so let's assume that phi from say some omega to phi of omega is a diffeomorphism. This I am assuming because determinant is non-zero. So, there will be some open set containing x naught. Okay. The inverse map, this implies there exists an inverse map sending x comma u to x comma okay. So, this is because the first coordinate phi, remember it was defined as x y going to some x comma u. So, I am just first coordinate. So, inverse now I we write everything in u coordinate, inverse will have first coordinate, is second coordinate only matters. So, now consider, let us call this as u, maybe I would use this notation somewhere, but does not matter. Now, consider the map consider the map say call it let us call it f from u to r to n given by x comma u going to y comma v, where y equal to minus f x u and v is equal to and v is just okay. So, v tilde and v tilde of x u is v of x f of x u. Okay. So, this is my map, and now or let us just call this as not v tilde, I have called it g. So, let me call it g of. So, this map is f and I have called the map g s is just v, but I applied at the point x comma minus f of x u, because f x u is now the f of x u is the new parameterization. Okay. So, then now I just compare, now I pull back my symplectic form which is the primitive. So, I have a symplectic form dx dy, and so I take its primitive and I look at the primitive say minus y dx, because d of minus y dx is this, and I pull back under this change of coordinate, then we get. So, remember, because psi is a symplectomorphism, since psi is a symplectomorphism, d of v du minus y dx equal to 0. Okay. And but we know what is this v du, v du minus y dx is nothing but the way in which I have constructed is f dx plus g du, where I am taking f in the variable x comma u, g in the variable x comma u, okay, because this is how I am transferring everything in change of. And but this means this is 0, that means this form is d of s for some s. Okay. So, this implies f equal to or minus and this is what precisely you check is the condition. Now, plug back this and you will get that y coordinate is minus ds by dx and
locally, so not simply connected, and that's why you can.
yeah, I am taking a small ball here. Yeah, this is 0 and I am just taking a ball on ball this equation, and so simply connected. So, what I have shown that this procedure, as long as you have some invertible map, you can do it. In case you have the this is non-zero, determinant of this non-zero, then I will have to change my coordinate transform. That will be a for example, if you have identity, then generating function will need this to be non-zero, and that is what Eliashberg is using. But whether you take x as coordinate or v as coordinate, we can write it as some d of s up to coordinate change. Is it clear? But now, okay, now this is existence, but can you kind of say something explicit about the generating function? And so next I want to kind of give an explicit formula for generating function for symplectomorphism that are obtained by flow of by time t map of a Hamiltonian flow. Okay. But I will give the explicit formula under this assumption. If you have other assumption, then the formula correspondingly will change in the derivative you are taking. Okay. So we have r 2n omega naught and h t x y Hamiltonian. Let suppose psi equal to phi h be time generated by the associated Hamiltonian flow. Okay. So recall that Hamiltonian flow meaning I am just looking at the vector field x h on such that where d I am taking in r n direction, and because I am looking at this is my Hamiltonian vector field and here everything in explicit coordinate, if I kind of actually find this vector field x h, I will get the formula that, so the manifold is generated by x dot equal to okay. So now consider the following. Consider the following action integral. So on the space of all path, I consider the following integral. So you take this integral, which basically integrates this quantity along any path z t, which is given by x t y t, okay, between interval t naught and t 1. So what I want to claim is that under suitable hypothesis, if I have a Hamiltonian flow which sends a point, say, so I have a point x naught y naught and it went via some trajectory to point x 1 y 1, and so I have this x naught y naught going to x 1 y 1 is my let me write it as u naught v naught, x naught y naught going to u naught v naught is my transformation, and I have some assumption on my partial derivative, or I have just a blanket assumption that psi, the whatever transformation I obtain has this property that coordinate change in u direction by replacing y by u is possible. Then if you then the function s which I would like to express as a generating function is just the value of this at the point x naught u naught is just the value of this action integral along this path, the path which is minimizing the action. Okay. So, I just take the solution curve of the Hamiltonian equation and I just integrate this quantity, and whatever answer you get is gives a map from the coordinate space R to n consisting of x comma u to R, and that is my explicit actional function. So, in some sense this this action integral is sort of universal action function. So, you if you have Hamiltonian flow, you do not have to look for this function. If there is an up to constant, it will be this. Okay. Is it clear?
So by Hamiltonian equations you will diagram?
By Hamiltonian equation I mean this one, but I mean this is nothing but what Yasha said, that if omega is a form, then derivative of h, there is a correspondingly dual vector field, and this vector field if I write explicitly in the coordinate, it will look like this because the form is also explicit. Okay. So, let me prove this. This is so I want to just first I want to prove that this. So, suppose okay, suppose I have, so one proposition I want to prove that the curve that minimizes phi among all the curve with fixed endpoints is the curve which satisfies Hamilton's equation. So, if I take a pair of point x naught y naught and x 1 y 1, and I am looking for or rather and I am looking for all paths between them which minimize that, which exists or not I do not care, but it minimizes that. Then if there is a minimizer, then that minimizer actually solves the differential equation. Okay. So, it is a kind of usual like least action principle. Yeah. H is given. Yeah.
So you are minimizing phi h.
You are minimizing phi h. Yeah. H is given, you are minimizing phi, and this form is given. I mean, this is just y dx, but I have just put t variable and written down, but it is just y dx. So, I will just hint the proof is like usual calculation. I just need to look at some vector field. So, let so, I look at just the parametric family of curve with fixed endpoint as we do in minimizing problem, and I call so notice that I mean S is a variation. So, this x and y are vector field along the curve for which you are varying, yeah, and phi at h I have just written as the derivative at x equal to s equal to 0 of the whole integral, okay. And if there is a curve that minimizes, it means this phi at equal to phi at is 0, okay. So, if there is a curve, so now differentiate the phi h in so let us just call, we know that phi h of z s is some and I differentiate with respect to s this whole quantity and look at s equal to 0, and if s equal to 0 this curve is minimizing, then this term will be 0. So, then this my definition says is equal to integral whatever this integral is, correct. And if the curve was minimizing at s equal to 0, this is 0, and now I just want to evaluate this by pushing d by ds under the integral sign. So, this will give me this and as is done usually in this minimization thing, we just evaluate this by using product rule, where we apply product rule when we want to kind of, we do not want this x double dot to appear. So, we apply product rule in such a way, and then we get that this 0 is nothing but integral T naught to T1 y into x dot minus plus So, just plug in the values, and now of course, we have variation with the fixed endpoint. So, this term vanishes, because we have all the we do not have my chosen vector field is such that it is 0 at both the endpoints. So, x t naught and x t naught and x t 1 are 0, and therefore, this reduces the problem. So, this since we have variation with respect to fixed endpoint, we get 0 is this integral but of course, this will be true for any kind of variations. So, in some sense any family, any vector field you take along this curve, as long as it is 0 on both endpoint, and I take, it will achieve this this fact that this integral minus this integral is 0, and this means by choosing my x and y, I can independently ensure that both these terms are 0. So, since this is true for any x and y, because I can decide how I am going to vary my curve. So, I can change the way in which I vary my curve, and this will imply that x dot is equal this is 0. But this is what precisely our equations were, and so I showed that the minimizing curve is actually the solution curve of Hamiltonian equation.
There will be a h dt.
No, I am not writing dt. I mean, okay, everywhere this is x. So I am just shortening my notation. I mean, this is not okay. You want okay. Y dot t x dot t minus h t x y dt. So everything is there, but I have just short.
Actually, you just wrote dx, so I thought maybe you have cancelled.
No. This dx is some set x dot dt. That I have not written that. But what you are looking at is a form summation yi dxi. So I just shorten the notation.
And so then there is that s, right? D del h del s.
No, this is y. Sorry. Because I am differentiating with respect to s. So here there will be h will have t x s y s. So there you will apply chain rule exactly. Anything, is it clear? But this formula is now kind of important for me. Okay, so now what we have shown that this action integral is actually minimizing something, and when you differentiate at least this phi hat in general, if it was not, even if it was not a minimizing curve, this phi hat of f is this property. Okay. So now what we do is, now we, to show that this is a generating function, we start with we have a symplectomorphism that takes point x naught y naught to x 1 y 1. So, and we have this trajectory coming from the Hamiltonian flow. We just vary now, do not keep the end point fixed, but just vary along these trajectories. So, when you vary along these trajectories, this term will continue to hold 0, but here there will be non-zero term, and you just check that non-zero term it would precisely imply what we want, that the coordinate y is minus dh partial derivative of this with respect to s, and the other coordinate is that derivative. Let me just write down, but it is just now that you know that you have got this minimizing curve, I just kind of move now. Do not keep the end point fixed, but just move along those minimizing curves and understand what is the equation I am getting, differentiate the this function, and you will see that it precisely gives you generating function. So, as derivative of that this function. So, let me just write down. So, under our assumption on psi equal to say phi, okay, under our assumption on phi T1 T2 H, we want to claim that x u is a and as I told you, proof is that you just vary this sh along this solution curves, because you see my function sh is given as I just integrate along always minimizing curve. So, when I want to take its derivative in s direction, I just vary everything along, I vary the endpoints of this function along this some by some vector. Okay. So, proof, choose sorry. I have made mistake in my notation, 1 second. So, I want to look at I want to look at S at these values x naught plus S x naught and u naught plus S u naught. Now, I can regard this function S as a function of x and u because of this uniqueness assumption I had told you, that I can change my coordinate and only work with the first coordinate of value and first coordinate of my domain. Yeah. So, therefore, this makes sense, and now I need to sort of differentiate this. So, where now S x is defined via z x z s, where for each s z s is minimizing. That means it solves the Hamilton's equation, and now you just apply the formula of this S h into this, because I am varying along the minimizing curve. This term is always going to be 0, but the endpoints are not 0, and you just calculate the value of what happens at endpoint. You will see that since endpoints are not fixed, but variation is along minimizing curve. Because for the definition of S h as a function of x comma u, we are only looking at minimizing curve. We get that just all that everything vanishes, but here the vector along which I am varying does not vanish. So, I get this term, and this implies y this implies y is equal to ds by dx with minus sign, and this is what my starting definition of a generating function was, that it appears as a graph of d of S h, where d of S h is now defined via this procedure. So, this way it shows that the generating function can be explicitly obtained once you have this solution for Hamiltonian equation. So, you can vary the solution. So, in that sense it is universal, and as I said that this assumption which I made, if it is not satisfied, you have to change this argument and look at the other determinant. So, then you will get generating function by this procedure for even identity map, and you perturb that identity map and you get generating function. That is the generating function precisely Yasha is using. So, that also has this appropriate action integral as its generating function. Yeah. So, so now you can regard this whole action function as a some map from space of path to this, and this function as a this generating function as a space of path to R is in some sense quadratic, which Yasha has explained me, but I have not understood. So, I will ask him to explain. Yasha, I have reached the point where you have to now go to the space of paths.
What I just kind of wanted to I ask Dishant explains is that there is a so there is this idea of extension of the generating function, and there is this, well, it's a kind of like I would say heuristic a little bit argument, but but showing that there is some. So remember, this construction give you generating function, but then the longer you move, the space grows, right? The dimension of the space grows, because each time I have a path, and if I need to a little bit more extend this path, then I have to multiply by space again t star of Rn, more copy, and so kind of like it grows, and so kind of the longer you have the have this. And there is some kind of canonical version of this, which kind of come from mechanics and come, but it kind of come canonically in infinite dimension instead of this finite but growing, but it kind of come immediately infinite dimensional. In some sense, what in the kind of original paper Cohn-Litzender did, it was, you can kind of read it as some kind of like rigorous implementation of this infinite dimensional kind of idea. So again, kind of like I'll repeat what Dishant was saying, but kind of like very maybe slightly differently. So again, what is a problem we consider? That we start with t star of Rn, and in t star of Rn you start with zero section, and you deform this zero section by there is some Hamiltonian deformation given by some Hamiltonian function, time dependent Hamiltonian function, and you want to say, and suppose you will deform, maybe I will write for time t from some, maybe it would be interesting to have some kind of like fix some t, and maybe not necessarily a right one, but just anything. And so you moving, so you have some kind of corresponding Hamiltonian vector field. This one, which is like, maybe I will use this standard. So Dishant was writing like xy, but like traditionally, like if you have write in mechanics, they write pq variable, and so there is this kind of action function. So there is a, okay, so it's given p dot is equal kind of minus dht over dq, kind of q dot is equal dht over dp. So there is this kind of Hamiltonian equation, and you moving your Lagrangian using this equation, and say that doesn't matter, but suppose it's with compact support or whatever. So in time t, our Lagrangian kind of moved, and kind of something like this became, right? And now we would like, so this is our LT, and we would like to, or the L, say T capital, like in time t, and we would like to write this some kind of God-given generating function, not inventing something, but just write this one. And now what like least action principle in mechanics, which Dishant was proving, what it says. It says the following thing, that so how this kind of mechanical system moving in the phase space? It says that like if you have a suppose you have a, say suppose you have a you need to have any kind of two initial condition in the phase space. So you have like suppose you have a two, say, Lagrangian submanifold, and you would like to understand Just a second. Yeah, kind of like standard formulation of least action principle in kind of how mechanics. It's formulated that if you have a, say, 2 points in configuration space, if you consider 2 points in configuration space, so that means that you have a cotangent bundle of some manifold here, Rn is configuration space, and you have a 2 points. And then kind of system somehow moving, and how this moving? It moving to minimize action functional. And action functional, like you have a Lagrangian, formulation of action function. This is a integral of some Lagrange function kind of along some path. But there is also Hamiltonian reformulation of action functional, and it's kind of like equivalent to the following. So you take in this take this 2 point. You suppose you have a 2 point in configuration space, but then let's consider. But you do not fixing phase. So you take a kind of like take 2 fibers. So this is our cotangent fiber over Q0 and cotangent fiber there. And now you would like to understand what are trajectories of our Hamiltonian system, such that you kind of minimize. So you want to take a trajectory between this fiber and this fiber. So not you fixing coordinate in the configuration space, but not in phase space, right? And then on the space in cotangent.
Fixing position and moment.
Fixing position, but not magnetic. So therefore you have this one, right? And then that you say that when you take an action functional and in Hamiltonian it's just integral of pdq minus ht dt, and you integrate over all paths around this one, then extremal of this, not it's called least action principle, but in fact it's not necessarily least action, but extremal point of this functional are precisely trajectories of Hamiltonian system. So this so there is some kind of Hamiltonian path and kind of here, and anyway choose trajectory of Hamiltonian path to minimize the function. So that's a least action principle. But now if you analyze the proof says what here I just choose fibers, but you can replace this boundary condition by what? You can replace by any, if you just kind of like standard calculus variation, essentially what Dishant was proving, then what the condition, kind of like boundary condition allowable. It's not true that like if I pick in like 2 Lagrangian submanifold and trying to find extremal with boundary, but you need Lagrangian submanifold with a property where this form PDQ itself vanishes. So it's not sufficient that dPdQ vanishes, but you need PDQ. It has to be 0 for this one. And for instance, there is another choice of this one. You can notice that if you take a fiber, on fiber PDQ vanishes. But on 0 section, PDQ is also vanishing. So therefore, if you, instead of this, you set up like you take a 2 fiber and say 0 section, and trying to take extremal with this boundary condition, then again it choose trajectory of Hamiltonian system. So let's return to our picture. So let's consider the space. So I want to just write some kind of generating function for this one. So what that mean? That I want to take my manifold, in this case Rn, my configuration space, and times some r of very big dimension. So okay, I just write some space E, and this space E will be infinite dimensional. And this infinite dimensional space will be the following. So I like define before just presenting this way. I will let's call this product which I will define. I will call maybe letter P, and this letter P is the following. It's the space of all paths which start on 0 section, parameterize from 0 to T capital, and go anywhere. So you have a space of such paths. And on the space of this path, consider action functional. So E to R, P to R, which is a just integral S of gamma is equal P dq minus integral of P dq minus HT dt. Okay?
This is this bottom line is some Lagrangian on which form vanishes.
It could be any Lagrangian form vanishes, but in this case I just take a 0 section. So I take Rn and take all paths which start of 0 and end kind of I don't know where.
I'm saying you are taking P equal to 0 or Q equal to 0?
What?
Are you taking P equal to 0 or Q equal to 0?
P equal to 0. I take a 0 section. You start on 0 section and end anywhere. So take the space.
P equal to 0, right?
What?
We took P equal to 0, right?
On 0 section, P equal to 0. Yes? Okay? Okay? So this is the Q coordinates and this is P coordinates. Okay? So we have this, and so now okay, so now, but I want to write this space P as a product. And it's a product of the following thing. So I want to write this P as a product of Rn times this what I call E. And E is the following thing. You take a again you have this Rn, and in Rn there is an origin. And like take a fiber over origin, so it's a Q equals 0. And take kind of all paths which start here and somewhere on 0 section and end on this space. So this is our E. And then of course if you so now if I have any path which start at some point, you just do the following thing. You take a projection of our space P to Rn. You just take a P of gamma. So you take gamma at endpoint T, and suppose this projection to 0 section I call not P. Is there any letters except pi and P for denoting projection?
Short form. Here.
Okay, so this projection of Rn to 0 section will be PR. Okay. So take a gamma of T and take a PR of this. So this belongs to Rn, right? You take any path, take endpoint projected, right? And so now, like, you take this path, and I coordinatize this path. So its first coordinates q will be precisely this my PR. And so now what is the second coordinate? Now I take this path, and I kind of like parallel transport it end point to 0, and then this is my element of this one, right? So I think about this vibration as this kind of product, right? So you have so you have the space P, and now you, and I have a, so therefore I can write so, and then let second coordinate I call, I don't know, whatever letter. I will call it eta at the morning. So therefore it's a function of q and eta. So you have a function of q eta, and I want to say now the following thing, that the claim that this is a exactly universal generating function, namely that my Lagrangian LT is given by formula that equal P is equal ds over dq, and ds over d eta is equal to 0. So this system of equation define me LT. And that's a kind of like what Dishant proved, right? Because this is because when I have a, so what it means? It just means that what you have this our Lagrangian, and this Lagrangian kind of like, so if I take kind of like this point Q and consider what are extremal of action functional over all passes with the boundaries this here, this precisely trajectories. And trajectories are exactly in one-to-one correspondence with intersection of our moved Lagrangian with this fiber, right? And so therefore, for every such thing, you have ds of d eta is equal to 0. That's least action principle says. And now, why p is equal ds over dq? So you need to just, okay, so this is computation. Again, Dishant was doing that. In this point, this ds over dq is actually equal p. So this is okay. So now I just want to add one more thing. So I claim that this is a function, precisely function quadratic at infinity. So let's check why this is a quadratic at infinity function. So this is, of course, will not be rigorous because it's an infinite dimensional space. So I need to kind of like, in order to really do you, I need to, I don't know, introduce some, I don't know, Hilbert or Banach. What?
If the Hamiltonian is compactly supported, then it's sort of, it's just integral PQ
Yeah,
dot.
okay. So I'll do it, but certainly you okay. So you need to do something in order to make it mathematical statement. But nevertheless, so let's so what I want to understand, what kind of how this thing look at infinity. So therefore I want to coordinatize this space E. And remember, the space E is just space of path kind of like with end here. So I can equivalently do the following thing. So instead of this quarter thing, I'll just complete it this way. So I take a identify T instead of this this quarter with this end. I'll just reflect it this way and reflect it this way. So you get, I want to consider loop, which is, I want to consider a loop which kind of centered at 0. Right? And you have a space of loop centered of 0 and symmetric with respect to rotation with basically P and Q. Right? So now you have a space of loop. Well, they parameterized 0 to 2, but I can change. I want to reparameterize it for 0 to 2 pi. So I just change parameter by 2 pi over t. And like let's assume that t equals 2 pi to kind of simplify notation. No, I want that so this thing is parameterized from 0 to pi over 2 I want. Such that the whole loop parameterized from 0 to 2 pi. Right? So then I take this any loop, any such loop, okay, eta, right? I call it eta. Take this eta, and eta is a loop, because I think. And I write it as a Fourier expansion. So I write this as a ck e to the ekt from minus infinity to plus infinity. Right? So that's every such loop. Okay. So this ck are coordinate in this space. So now this is all loop, but this is not all loop because it's symmetric loop. And you can just immediately check what does it mean. What is the ck is complex numbers. But what the condition for Fourier coefficient are implies that this is a thing symmetric with respect to this reflection in respect to minus reflection. And you can check that it means that first of all ck have to be real, and second that all odd coefficients are 0. Only even coefficients. That's precisely if and only if it has this symmetry. So you have this kind of ck e to the kt, and all ck real, and all of them only even kind of harmonics. And now, and you want to compute what is PDQ minus HTDT. But let's just forget about PDQ minus HTDT. What is just is compute what is the integral of PDQ over such kind of loop is. And so, okay, so this is just compute area, which kind of easy. And okay, you just do this computation, and if I'm not mistaken, kind of like what this computation, you get this. So you get k ck square. So this integral is equal to. So you get this precisely kind of indefinite but non-degenerate quadratic form. But then plus HCDT. But you see this kind of like in all this infinite dimensional setup, this so this is a kind of bounded. So it's kind of quadratic with respect to this higher harmonic Fourier coefficient, and HCDT is in fact not dependent on derivative of gamma. So this is in terms of any kind of reasonable norm, this is a bounded addition. So it's precisely non-degenerate quadratic form plus some bounded addition. And so that's what we have. And kind of like what Conley Center was doing is essentially precisely this, kind of writing this, but then just showing that you can cut off like higher kind of high term, higher harmonic, and this, and still have the same kind of critical point. So that's what.
From this point of view, what we saw earlier in the morning was just that you're partitioning the path into small little paths. That's a finite dimensional approximation of the path.
Yes, finite dimensional approximation. Yes, indeed. So there is a kind of like and this is what was precisely Chaperon was doing, kind of like after proving of proof of there is a this like again in variational calculus there exists kind of like it's called method of broken geodesics. So instead of kind of like minimizing over space of all paths, you can just partition interval by kind of small geodesic or kind of small Hamiltonian trajectory, and just kind of piecewise doing this, and then kind of like theorem which they prove that kind of you have a partition enough, then critical point are the same. So that's okay. Okay, any question?
I didn't understand what you said.
What?
This last thing you explained, I didn't understand. How it is related to dividing path into.
Okay, so here the, like when you're doing this in so let's go to Riemannian geometry.
Yes.
So in Riemannian geometry, you like geodesics. You compute as I said, like Lagrangian formulation of this Hamiltonian H principle is that you kind of you minimizing length through all paths. But then, like theorem in textbook on Riemannian geometry is the following: that it's not to find geodesics, it's not necessary to minimize over all paths, and you do the following thing. You consider piecewise smooth geodesic paths. So you just take a kind of this and you take a minimum or over all of the same integral of such path. And now this is a finite dimensional space if you kind of partition. And kind of theorem that if you partition, yeah. And in the context, if you reformulate this principle in Hamiltonian formulation, it means the following thing. So we consider this space for here, but instead of such thing, you're doing the following thing. You put a lot of kind of intermediate fibers, and you consider discontinuous, because in phase space, your derivative is discontinuous here. So what you do, you consider like Hamiltonian trajectory here, plus Hamiltonian trajectory here, kind of like, so you consider such path, and now we minimizing over this finite dimensional space, and again theorem that extremal the same. So then
paths you are varying. You
What?
cut down the paths you are varying. Instead of all possible paths, you just look at this kind
yeah,
of.
only on this path. So you have only finite dimensional space of path, and that's what Chaperon did. It's kind of like concrete. Okay, so any other question?
So in this calculation on Rn, we had that action integral which would give us the generating function. But the setup that we talked about in the morning was the general setup. So we have any such action integral in the
No, but in what I was talking this morning, yeah. Also, you see, what we were doing this morning. Okay, so you have this.
Perhaps nothing prevents us from defining this action integral setup because it's formed.
What is the general? So I understand what you.
So you had this T star n. Oh, or maybe I perhaps I'm wrong in the first step. I will always assume your n is close manifold, and then you can assume that.
Okay. So in principle, the question why we care about Rn and not doing the same thing for like any symplectic manifold, right? Why? So you can kind of say the same thing. So suppose you have a Hamiltonian isotopy, say, on any symplectic manifold. Let partition this Hamiltonian to small one, and instead of each one, you have this kind of like product, and so therefore, so and neighborhood of diagonal is actually cotangent bundle. And therefore, you can say, well, you do the same thing. But there is a crucial difference between this case and that's what and Rn, because you know what? Because in order to do that, we need, remember, we were choosing some polarization. We have alternate polarization. So Rn has an enormous number of polarization. You can choose this Lagrangian, this Lagrangian, and in general manifolds we cannot do this. So that's kind of like a difference between Rn, why this kind of work perfectly in Rn. It does not work like on the spot. In other manifold is a not so many polarization.